Hi there. In this video, we'll look at the second derivative test from lesson 4.3. And I've selected a homework problem from page 216. This is problem 36. And directions indicate we're to use the second derivative test to find the local extrema for the function, and we're given this equation to analyze. Okay, a couple remarks about the second derivative test in general, and then we'll do that specific problem. So the general problem here is to identify local maxima and local minima of a function, and there are really three ways to go about that. Number one, you can look at the direction in which the graph is moving. If it changes from up to down, you know that represents a max, and if it changes from down to up, you know that represents a min. So we can use the direction, rising, falling, signals max. If it falls and then rises, that signals a min. So if you have some way of determining where a graph rises or falls, you can figure out the local extrema in that way. The second way involves the concept of slope. And we know that at a local max or min, that there may be a horizontal tangent like you see here. And the question is, if the slope is 0 in both cases, well, how do you tell them apart? And the first derivative test has the answer for us. If the slope of the graph is positive and then becomes negative on the other side, then that would signal a max. Whereas, if the slope is negative and then becomes positive, that would signal a min. Here it is again. Slope changes from positive to negative, signaling a max. Slope changes from negative to positive, signaling a min. And because the slope is found by computing the first derivative of a function, that is called the first derivative test. All right, that brings us to the second derivative test, which involves the concept of curvature. So the third way in which you can determine the behavior of a function in regards to its local extreme values is using the curvature. Are you bending down? Then you're a max. Are you bending up? Then you're a min. Okay, in technical terms, if you're concave down, then there's a max. If you're concave up, then there's a min. And of course, all this assumes that we're looking at a point that has a horizontal tangent line. Okay, the curvature is determined by the second derivative of a function, so this is called the second derivative test. All right, and here's a summary of what was just said. If you want to apply a second derivative test, you would first start with the first derivative, and that then tells you where the critical numbers are. So we want those values that have f prime equal to 0, and now we know we're looking at one of these or possibly one of these. And we use the second derivative to figure out which. So we want to classify that as a local max or min, and here's what the second derivative test says. If the second derivative at that critical number is positive, all right, that would signal to us that the graph is concave up. That's called the concavity test from a previous discussion. When second derivative is positive, the function's concave up. All right, if the function's concave up, then visually that would be this situation, and you know that you're dealing with a min, not a max. All right, and here's a related situation. Again, we have a horizontal tangent line. We want to determine which kind it is. If the second derivative, though, is negative, then that would tell us that the function is concave down, which would signal visually a local max. Again, if you're concave down, that's this. And so you're looking at a max point, not a min point. Okay, so with all that theory out of the way, let's actually get to the problem and see how that looks. Okay, so step 1 is the original function. Step 2, let's start computing derivatives. Here's the first derivative of the function. Okay, and we'd like to stop off. Why don't we just continue on and do the second derivative, and then we'll stop back and do whatever else is needed. Okay, so there we have it. Now I'd like to stop off and figure out where is this expression equal to 0. And that will tell me where the critical numbers are. So in order to do that, I'm going to go ahead and start factoring things. So I see that 15 is a common factor of all these numbers. So let's go ahead and pull out 15 from each term. Okay. And I still want to know where things are 0, so I'm going to try to continue factoring with this. And this is kind of an unusual situation. This is a factoring skill that is not often used. But it looks as if we can break this down as follows. If you multiply x squared times x squared, you're going to get x to the 4th. And if you multiply 1 times 4, you're going to get 4. And if I make it this way, I'm going to get 1x squared and 4x squared, and that makes 5x squared. All right, so it does factor kind of like a trinomial factors to the product of two binomials. All right, so again, that's kind of a rare factoring skill, but it did come into play in this problem. All right, and I can do some more factoring with this. I still haven't found any critical numbers, so I need to continue the process of factoring. X squared minus 1 can be factored, and x squared minus 4 can be factored. And now the critical numbers are just on display. This expression will equal 0 when x is any of the following 4 values. All right, so we found 4 critical numbers for this function. And our next job will be to take each of the critical numbers and throw them into the second derivative to see if the answers are positive or negative, and then we'll know which are maxes and which are mins. So let's go ahead and do that. Okay, can I just make some room for this next step? And I will again use factoring because I feel like that's going to make things easy in this next step. So I'm going to factor out some stuff. Can I factor out 30 from both of those? Okay. And again, I've just done the factoring because I feel like that's going to make the next step easier. Okay, so if I plug in, so now it's time to start plugging in values. And if I plug in this first critical number, which is 1, let's see what we get. And all we care about is the sign. We don't actually need to compute the numerical value. We just need to know if it's positive or negative. So when I do 30 times 1, you're getting a positive answer. And when I do 2 times 1 squared, that's 2. Take away 5, that's negative. And so when you multiply those two things together, the result is negative. And according to the second derivative test, since y prime of 1 is 0, that tells me there's a horizontal tangent there. And when the second derivative is negative, that tells me the graph is concave down. So I'm picturing this, and I just decided that when x equals to 1, Will Rose, when x equals 1, we should expect to see a local max for this function. Okay, and that's how the second derivative test is used. All right, so the rest of this now is just going to be more of the same. I'm going to plug in each of the critical numbers and figure out what goes on, and then we'll look at the graph and see how we did. So here goes. Let's now, and I'll save a little bit of space here by just using my eraser. Okie doke. And perhaps I should start to organize these on a number line, like in order, so that we can visualize what the graph really looks like. So smallest, next smallest critical number, and here's the biggest critical number. Okay, and we just analyzed x equals 1. We determined that there was, we should expect a local max there. So let me just go ahead and draw that in right there, and then we can make some room. Okie doke. Okay, next. All right, again, we're just going to go down the line now. So next we have critical number -1. 30 times -1 is negative. And if you plug, wait a minute. Sorry. 30 times -1 is negative. And if you plug -1 in here, you're going to, again, get a negative answer. And so the product is positive. All right, so we have that y prime of -1 is 0, signaling a horizontal tangent. The second derivative is positive, so that tells us the function's concave up. And so we're picturing this, which is a local min, and that occurred at this critical number right here. So at that value, we're expecting to see a local min. So it's going to look like that. The graphs probably join up somehow, so we'll just connect them that way. All right, 2 down and 2 to go. Let's keep it rolling with the second derivative test. Fun times. Okay, so next we are on this critical number right here, which is 2. And I want to throw that number into the second derivative formula. 30 times 2 gives a positive answer. 2 squared 4 times 2, 8. Take away 5 is positive. And so the product is positive. So y double prime of 2 is 0. Gives me horizontal tangent. Second derivative positive. Concave up. So we are picturing them in at x equals 2. So let's go ahead and put that in our picture. And here's the min happening. And we'll just connect these graphs like that. All right, and it's probably concave up forever. So we're going to continue up like that. All right, 3 down, 1 to go. Let's keep it moving, keep it moving, keep it moving, keep it moving. All right, last one. We now have to look at -2, which is our fourth critical number. So we'll throw that into the second derivative. -2. Okay, 30 times -2 is a negative number. -2 squared, 4 times 2, 8, take away 5 is a positive number. I didn't mean to say -1 here, just negative. Okay, and so the product is negative. And so let's see what's up. Whoops. Y prime of -2 is 0. Horizontal tangent. Second derivative negative. That tells me it's concave down. And so we're picturing this situation, which is a max. And that will occur at this critical number, which is here. And so let me go ahead and draw that in. We do have a local max there, and the graphs connect. Okay, so we're expecting the graph to look something like this. Down from infinity, up, hump, down, bump, up, hump, down, bump, and on up. But let's go ahead and check the graph to be sure that things are making sense. And we should expect to see critical numbers at -2, -1, 1, and 2. So let's pop over to Desmos, and let's see if all is well from that perspective. Okay, so here I've typed in the formula for this function, and I've set the viewing window so that I can see all of its interesting features. And indeed, there appears to be a critical number at -2, and at -1 as predicted, and at 1, and at 2. And each of those values does exactly what we thought it would. We've got concave down, signaling a max. We've got concave up, signaling a min. Concave down signals a max. Concave up signals a min. All right, so this second derivative test is a powerful tool. Knowing the first derivative and the second derivative of the function can give you an awful lot of information. In fact, we've pretty much figured out every essential thing about this graph just by taking its derivatives. And derivatives are useful. That's the whole message of this chapter. I hope this video was helpful in teaching you the second derivative test. Good luck and see you next time.